Water Quality Monitoring with Optical Methods, presented by Antonio Ruiz Verdún, in collaboration with Carolina Tenjo, José Moreno, and Vicente Caselles, from the University of Valencia, Spain. My name is Antonio Ruiz Verdún, and I'm Research Associate at the Image Processing Laboratory of the University of Valencia. I will present today an overview of the optical method for the water quality monitoring in inland and coastal waters mainly, which is my main subject of research in the last 20 years. This tutorial has been created with the collaboration of Carolina Tenjo, which is Research Associate at the IPL, University of Valencia, José Moreno, full professor of the University of Valencia, and Vicente Caselles, full professor of the University of Valencia. This tutorial has been developed free of charge for educational purposes only and without any commercial interest. The images and figures of this tutorial have been reproduced from open sources and are cited accordingly unless they were created by the author. If they may be infringing any copyright, please let me know to remove it in the next release. I will start this tutorial with an introduction to the optical methods for water quality monitoring in waters. I will give then an overview of the main optical properties of water bodies and of the methods for the remote sensing of water quality for obtaining different type of products and applications. At the end, I will give also an overview on the requirements for the sensors and platforms to study water bodies and the main instruments that are used in this field. So the first question that we can pose is, what does a remote sensor sees in water? And basically, a remote sensor is measuring a flux of energy, which is measuring watts, coming from a surface, measuring square meters or on other surface units, observed with a solid angle, that these angles are measured with a stereo radian, and for an interval of wavelengths. And then we have to introduce this nanometers or micrometers magnitude. So the magnitude that tell us the amount of energy that is being measured from the air surface by a remote sensor is given by the radiance, which normally is written with an L. So let's see what determines the observed radiance coming from water bodies, and therefore which type of water constituents can we study from remote sensors. We call optically active constituents to those substances or suspended particles that are in the water bodies and that affect somehow the optical properties of water itself. So that means they interact with the incoming solar radiation in different ways, and from this interaction the flux of solar radiation is being transformed within the water bodies. And finally, what we have as emergent flux is a modification. Is modified both in its magnitude and in its spectral shape. So obviously the first optically active constituent is water. Water modifies the incoming radiation flux through the processes of absorption and scattering, and as we also see later, also fluorescence. Water, as we will see later, absorbs very strongly light in the ultraviolet and in the infrared ranges. That means that most of the light in, or almost all the light in those parts of the spectrum is completely absorbed by water, and is going to be unuseful or not useful for the remote sensing of water bodies. But apart from water, there are other constituents that modify this solar incoming radiation. Most important of all, maybe, is the phytoplankton. Phytoplankton is very heterogeneous group of organisms that live in the water bodies, lakes, oceans, coastal waters, and is composed of photosynthetic organisms that can produce organic matter that can fix carbon, atmospheric carbon, and then transform carbon and water into organic compounds through the process of photosynthesis. And therefore, those organisms are equipped with a very complex photosynthetic apparatus, and this is made of different pigments that absorb selectively light of some wavelengths. So phytoplankton absorbs selectively light, and from this light it uses for producing chemical energy. But also, as phytoplankton are cells, are particles, sometimes with outer structures, membranes, or walls, and sometimes from calcite or siliceous walls, it also scatters light. So it absorbs light and it scatters light in different ways. But apart from phytoplankton, there's another complex pool of substance in water, which is normally named as color-dissolved organic matter, or CDOM. These dissolved substances basically only absorb light, and as we will see later, selectively they absorb light more strongly towards the blue and ultraviolet, and more slightly towards the red and infrared part of the spectrum. Another group of optically active constituents are suspended minerals. These are very important in coastal and inland waters, especially when there are influxes of rivers carrying the erosion of the continental erosion, and by resuspension of the sediments that are in the bottom of the lakes or the coastal areas. These particles, which are of mineral origin, and also detritus, what is called detritus from the decomposition of organic matter, are also a heterogeneous group that have properties of absorption and scattering. So they absorb and they scatter also light. So at the end, what we have is this complex group of interactions in which light is being modified, solar light is being modified through its pass through the water bodies. And at the end, what we measure is the part of this radiation that is backscattered, that is scattered towards the sky, and that's called the water leaving radiance. The water leaving radiance has information on the processes of absorption and scatter that have occurred within the water body. And through the water leaving radiance, we can decipher, we can go back and know what kind of substances were in the water body that we are observing. But we have to take into account that in the observed radiance, there are other contributions that do not come from the interaction of the optical active constituents, but mainly they come from specular reflection of light in the interface of water and air. And those specular reflections can contaminate the signal, and therefore should be removed somehow in order to study the water leaving radiance by itself. Apart from those basic processes, absorption and scattering, most water constituents also can emit fluorescence. As you probably know, fluorescence is a process of light emission that requires a previous absorption of electrons, of photons, excuse me, that produce electrons to go to an excited state. Those electrons come back to their base state, and part of this energy could be emitted in form of light. Water, for example, has this type of fluorescence, which is called Raman scattering, which is important, especially in ocean. Not that important in case of inland waters or coastal waters, because the signal is not very important in comparison with the signal produced by the other optical active constituents. Also, CDOM can produce fluorescence. Basically, in the both water and CDOM emit fluorescence in the blue wavelengths, while phytoplankton, basically due to the chlorophyll A fluorescence, but also the two other photosynthetic pigments, also emit fluorescence, and in this case the fluorescence is emitted in the yellow and basically in the red wavelengths. So this is more or less the scope of what can we see or what elements or what constituents are affecting the water leaving radiance. But there are important differences whether we are studying the open ocean or coastal and inland waters. And as I said at the beginning, this tutorial is centered mainly in the study of coastal of inland waters. In open ocean, waters normally are characterized by a low chlorophyll A concentration. Remember that chlorophyll is the main photosynthetic pigment of all photosynthetic organisms, and then is a proxy for phytoplankton biomass. Since the chlorophyll concentration per cell unit is rather constant. In the open ocean, far away from the rivers and other sources of terrestrial materials, the concentration of suspended minerals are typically very low, and also the concentrations of CDOM, organic matter. And basically this organic matter and detritus are very well correlated with chlorophyll A. That means that what we can find in the open ocean are small concentrations of phytoplankton, a small number of cells, and a small concentration of chlorophyll A, and also small concentration of CDOM, which are related with chlorophyll because basically they derive from the decomposition of phytoplankton. This type of waters in which all the optical active constituents are correlated with chlorophyll concentration. So basically the optical properties are only modified by phytoplankton are called case 1 waters. In contrast, coastal and inland waters are much more complex. Chlorophyll A, suspended minerals, detritus, and CDOM are very variable, and often in very high concentrations. So the concentration of chlorophyll, for example, can go in several orders of magnitude from zero point 0.1 to 100 microgram per liter, or even up to 1000 in very high chlorophyll concentration in what are called blooms of phytoplankton, or excessive or massive growth of phytoplankton. But not only the concentration of the optical active constituents can be very variable. We have also sedum high concentration, for example, typical in boreal or tropical lakes, in which there are a lot of organic matter which is being degraded, or a very high concentration of suspended minerals in riverine estuaries, or in some lakes, and in wind subject shallow lakes, for example. But not only, as I say, the concentrations can be very high, but also they are typically uncorrelated. That means that they can vary independently one of other. This is because, for example, in a lake, we can have autochthonous phytoplankton growing on the nutrients present in the lake, but due to the inflow of a river, we can have allochthonous or external sedum or suspended minerals, and the concentrations can vary depending on the water conditions, the flow regime, and therefore there are no fixed relationship between chlorophyll and the other optical active constituents. As I remember, this tutorial focuses on inland and coastal waters. Now, we will see the main optical properties of water bodies. Well, when measuring this water optics, there are two groups of optical properties. The first one are called the inherent optical properties, or IOPs, which are called inherent because they are measured in a way that they are independent on the radiance distribution within the water. When solar light enters in the water body, as I said before, it is subjected to absorption and scattering, and therefore water bodies are diffuse light fields, and the angular distribution of these light fields is rather variable. The inherent optical properties are measured under control illumination, as we'll see later, typically in setups with collimated parallel light. And they are very important because they are directly correlated with the nature and composition of optical active constituents. Some of these optical properties and the absorption or scattering coefficients, the phase function for scattering, and others. The other group of properties are called the apparent optical properties. This is the reason for this name is because they depend on the radiance field within the water body. These apparent properties are the properties that we can measure with radiometers or with sensors in different platforms, in a plane, or typically in a satellite, and therefore are the magnitudes that we will deal normally in remote sensing of water bodies. And well, the most important are the different reflectance, or for example the attenuation coefficients. Regarding the inherent optical properties, here I represent a typical setup for measuring some of these properties. As you see here, we have a setup composed of a lamp, a collimator that produces a beam of parallel light, and this enters into a cuvette in which we have in which we have water sample with particles and dissolved substance. As you see, the light entering in this cuvette is being absorbed, so it's being reduced in its amount of light exiting the cuvette, and also is being dispersed. If we put the detector in a position far away from the cuvette, what we measure at the end is the total amount of light that has been absorbed and scattered, and this is called the attenuation coefficient, C. If we put this cuvette inside what is called an integrating sphere, that means a sphere that is covered by a white, completely reflective material. What we can collect at the end at the detector is, as you see, the absorbed, the transmitted light, and also the scattered light, because the scattered light is being collected in the walls of this integrating sphere and converged in the detector. So this second magnitude is the absorption coefficient. In the first case, we are measuring the total attenuation of light, and in the second, the attenuation due to absorption only. In another case, we can see the rest, or for seeing the rest of light, typically we can, what is called the scattering coefficient, we can measure it just by subtracting absorption from attenuation. In this case, we represent in the two hemispheres the light that is being scattered in the forward direction and the light that is being scattered in the backward direction. And this light that is being scattered in the backward direction is called the backscattering. And the coefficient that measures the scattering of light, or the backscattering of light per unit of path length, is called the backscattering coefficient. So here we summarize the different coefficients which are expressed in inverse meters, because they are the attenuation, the absorption, the scattering, or the backscattering should be referred to a given path length. And those are the basic optical properties that can be used for characterize a water body. It is very important also regarding the scattering to know not only the total amount of scattering, but the angular distribution of the scattering. And this angular distribution, which represents the amount of scattered light depending on the scatter angle, is called the scattering phase function. And we see here two examples of the typical scattering phase function for water body with particles and chlorophyll, and in the right the scattering function of pure water. As you see, pure water has a symmetrical scattering in the forward and backward direction. That means that pure water is isotropic, while a typical phase function for an inland or coastal water body shows a very marked asymmetry in the scatter light, meaning that most light is scattered in the forward direction and a small amount is scattered in the backward direction, meaning that water bodies are typically highly anisotropic in nature. As I said, this is called the volume scattering function. The other group of optical properties called apparent optical properties from this other group, I will focus in the most important magnitude in the field of water remote sensing, which is called remote sensing reflectance. Remote sensing reflectance is basically the ratio between the water leaving radiance and the sun irradiance reaching the water bodies. And here I will summarize the typical setup for measuring this magnitude in the field. So here we see a radiometer with a field of view not very high, 8 degrees, and this is typically used for reducing the amount of diffuse light entering the lenses and not coming from water. We use a typically gray plate for measuring the incoming radiance, and this way we optimize the dynamic range of the radiometer, because reflectances of water bodies are typically low. So first we will measure the incoming solar irradiance, and here we have an example of a typical spectrum of solar irradiance in the visible and near infrared range from 400 to 900 nanometers. Then we measure the observed radiance coming from the water surface. As you see here, we use unit of radiances. And then it's very important also to measure the sky radiance. That means the diffuse radiance that is reaching the water body in the same geometrical or in the same observational conditions that the radiometer is measuring. And this is called the sky radiance. In the right, I represent also the optimum measurement condition to avoid very high reflection of sunlight in the water surface. That means that if we want to measure water bodies, we should avoid what is called the sun glint. That means the glint, the sunlight that is being reflected specularly by the surface of water. And this could be achieved measuring in angles of 90 degrees or better 135 degrees away from the sun. That means an azimuth angle of 19 to 135 degrees. So when we have measured these three magnitudes, we can obtain the remote sensing reflectance, which is written like you see here. And but before we have to correct the measured radiance, which we have called radiance from the surface, SFC, with the contribution of skylight, which is being reflected specularly by the surface. While we do this, and this reflectance of the surface, in the case of waters that are not in windy conditions, it's called the Fresnel reflectance. So at the end, the remote sensor reflectance is the ratio of the water leaving radiance after this correction and the sun irradiance. Here you see a typical, well, or not that typical, but a device, a handmade device using a radiometer that use a fiber optic for measuring remote sensor reflectance. So here you have this device that control the angles, the azimuth angles, by just projecting the shadow of the bar to see the sun direction. Then we can control also the zenith angle observation, excuse me. And this is very important because, as you see in this picture, if you look the water in the bottom part of this picture, you can see that the water has, well, typically turbid color, but as you go away and you look with a more slant angle, what you start to see is a higher contribution of reflected light. So the angle from which we observe the water is also important for minimize this contribution. Well, and here you see also the spectral that we uses this piece can be turned, and we can measure first the spectral and then the water. So, well, once we have seen basically the main inherent and apparent optical properties, it's very important to know which is the relationship between both. And why is this important? Well, because inherent optical properties are directly correlated with the optical active constituent of water. And it would be very important if we can also correlate the apparent optical properties, what we see from a remote sensor, from a satellite, with these inherent optical properties. And well, this is a basic equation of the radiative transfer process in waters, which correlates the remote sensor reflectance through a pseudo constant depending on several factors, the observational geometry, the geometry of sun, wind, several factors. So it's not a true constant, but it's rather constant under certain circumstances. And this remote sensor reflectance is directly proportional to the amount of backscatter light, and inversely proportional to the sum of absorption and backscattering. So this is the basic equation that relates remote sensing reflectance with the absorption and backscattering coefficients. And it's very important because the absorption and backscattering coefficients can be expressed as the linear composition, a sum of the absorption of the individual optical active constituents. Therefore, the total absorption coefficient of a water body it can be expressed as the sum of the absorption of water, the absorption of phytoplankton, the absorption of detritus, the absorption of suspended minerals, and the absorption of CDOM. And the same way, the backscattering can be expressed as the sum of the scattering components. Here, CDOM is considered to not scatter light. In this range of wavelengths, the dissolved compounds do not scatter light. So further, the absorption of a given component, optical active component, can be expressed as the product of the specific absorption coefficient plus the concentration of this compound. And similarly, the backscattering of a given component can be expressed as the specific backscattering coefficient plus the concentration of this compound. Therefore, with this set of equations, we can fully characterize a water body. All this will be the path for the analytical inversion of the remote sensing signal to obtain from the remote sensing reflectance the concentration of the different optical active compounds. So these equations are the base of the analytical or physical algorithms or models that describe the water bodies. Well, this relationship between IOPs and AOPs can be seen in this example. In the above graph, what we see is a typical remote sensing reflectance spectrum from an inland water body, which has a chlorophyll concentration, a relatively high chlorophyll concentration. We can see here several peaks and faults that are due to the selective absorption of different pigments. Here, what we see is the different absorption and scattering coefficients of the optical active compounds. First, we can see that the water absorption is very low in the blue, green, and towards the red, but in the red, and especially in the infrared, it rises sharply. And this produces a decrease in the remote sensor reflectance in the infrared. So basically, the absorption of the different optical active constituents produces a reduction or produces those minimums of reflection or those minimums of reflectance in the reflectance spectra. We also see here a typical absorption spectra of spectrum, of phytoplankton, in which we see a peak here in the blue, which is caused basically or is basically due to the absorption of chlorophyll A and other photosynthetic pigments. Another peak here also in the red, which is the other main peak of absorption of chlorophyll. And we will see other small peaks in other due to other pigments. Here in yellow we see the typical absorption shape of the sea dome, which decreases approximately exponential or potentially from blue wavelengths and ultraviolet wavelengths towards green and red wavelengths. And this also is a typical absorption spectrum of detritus. And here in the same with the same scale we can see the total backscattering coefficient of this given water body. These are also all of these are field measurements in a given water body, in a given lake. So as you see, basically the absolute value of the reflectance will be determined by the backscattering, and the shape will be mainly determined by the absorption of the different compounds or the different optical active constituents. So as we see, we can see this maximum of absorption in the blue at 440, which is seen as a minimum of reflectance in the reflectance spectrum. Then the relative minimum of absorption of the different compounds or constituents is reflected as a peak in the reflectance spectrum. The other maximum absorption of chlorophyll at 675 can be seen as this minimum. And also, for example, in this case, we can see also the absorption of phycocyanin, which is another photosynthetic pigment characteristic of cyanobacteria, a very important group of phytoplankton. And this peak, which is also very important, as you see, reflects the combination of a decreasing absorption of phytoplankton and an increasing absorption of water. And also in this peak, we can see the contribution of chlorophyll fluorescence. Here we can see three different examples of reflectances measured in inland waters in Spain. In the first case, the blue one, is measured in a relatively clear reservoir, a relatively clear lake, and you see that the reflectance is has a peak towards the blue and decreases towards the red. And basically that means that this water body will have a blue aspect. The yellow one is a spectrum measured in a highly productive lake. That means that the concentration of phytoplankton is high, and you see that the shape of the spectrum is much more determined by the absorption of phytoplankton. And the third case is a similar case, or a transition in between the two. So here you can see the effect of the absorption of chlorophyll A and carotenoids that add other photosynthetic pigments. In this region is where the absorption of sedum determines more the reflectance spectrum. This minimum of absorption, relative minimum, can be related with phycocyanin concentration, while this other is directly due to the chlorophyll A concentration. At the end, the particle scattering could be measured in the infrared, because in this region the absorption of optical active constituent is minimum, and therefore the absolute value of reflectance will be basically determined by the particle scattering. Here you can see several examples of the shape of the reflectance spectrum or spectra that can be measured under bloom conditions. The blooms, as I said before, are a massive growth of phytoplankton, which occur when the nutrient concentration in water are very high, and phytoplankton can grow in a very rapid way, giving the water this very turbid and green aspect, and in some cases with aggregates of particles that can be seen by the eye or can form scams in the surface of the water. These are the more extreme conditions that you can find in inland and coastal waters, but are also very important to monitor in terms of water quality, because the effects of these massive growths in the health of the lake ecosystems and in the impact in human activities is very important. Well, once we have seen the different optical properties and how water bodies can be studied with the reflectance measurements from remote sensors, we will see very briefly, because this is a very wide field of research, the main methods for this remote sensing of water quality. So basically, when we want to study the water quality from remote sensors, what we have to develop are algorithms that transform these observed radiances and reflectances into maps of concentrations of the different optical active constituents. And one of the main optical active constituent studied is phytoplankton through the chlorophyll concentration. Well, those algorithms can be purely empirical. That means that we measure both the reflectances and the concentrations of the given constituent in water, and we obtain a statistical relationship between both through, for example, linear or nonlinear regressions, and we obtain a mathematical model correlating the concentration of what we want to study and the reflectance. These are very useful for studying a given water body if we have the information, but typically are very limited in space and time. That means that if we obtain a given mathematical relation from a lake, which a particular set of optical constituents and optical properties, it would be very difficult to obtain good results in a very different lake with different optical constituents and optical properties. The other type of algorithms are the analytical ones, which are based on the inversion of radiative transfer simulations. If we know the IOPs of the water bodies, we can simulate from those IOPs the apparent optical properties, and we can reproduce the process of radiative transfer through the water. With those simulations, we can really, by an inversion of those simulations, we can really reproduce very accurately the behavior of a wide range of water bodies. And therefore, the models obtained in that way by the inversion of forward radiative transfer simulation could be representative of a very wide range of situations. Therefore, this could be the most interesting algorithms for water quality retrieval. The problem is that they require a very deep knowledge of the inherent optical properties, and this is not easily achieved because the variability of optical properties in water bodies is quite high, and the amount of available data is not that high. Therefore, a third group of algorithms that are between the two are those called semi-analytical, which are based on non-relationship between the OLCs and the IOPs. And basically what they do is to simplify the analytical models by parameterize some of the those relationships. So there are simplification or analytical models based on realistic assumptions. Well, many of the algorithms are based on spectral indexes that relates the reflectances in different parts of the spectrum. And one of the most used is the region in the red and near infrared range, in which, as we saw before, the chlorophyll absorbs light very markedly, and the other compounds, the other OCs, absorbs very slightly. Therefore, what we do, and this is an example of a band ratio algorithm, or an algorithm based on a band ratio for chlorophyll, what we do is we look for a wavelength in which the reflectance is related with the absorption, and this will be the this one, the first reflectance, and the second one is a reflectance in an area in which the absorption of this compound is minimum. So this could be considered as a reference band where no absorption occurs. And therefore these algorithms relate the chlorophyll concentration to this ratio. Another type of models, well, I should say that there sometimes the ratio to minimize the effect of absorption, of atmospheric correction, of other errors in the retrieval of reflectance. Sometimes the ratios are expressed as normalized ratios, the type, for example, of the NDVI in land surfaces. In this case, what we show is an example of a baseline model in which it's a similar approach, but we use three wavelengths, two reference wavelengths from which we can trace a baseline, and a third reference, a third wavelength in which the absorption of the chlorophyll occurs. And therefore, excuse me, by measuring the magnitude of this peak under or over this baseline, we can relate this magnitude to the chlorophyll concentration. Well, it's very important to take into account when we apply any algorithm to obtain chlorophyll concentration or suspended minerals or CDOM or other pigments, which are the typical objectives of these algorithms. It's very important to know that we first must remove what we can call error sources or contributions that are not coming from water leaving radiance, but are coming either from the water surface, from the atmosphere, or from the land or the pixels surrounding a given pixel of water. So here we represent a remote sensor with a field of view, and this represents the field of view of the sensor, let's say a given pixel, and therefore this is what we observe, and here we represent the water leaving radiance. That means the radiance that is going out from the water with the information of the OCs, which is propagated through the atmosphere and as is attenuated both by the absorption and scattering of atmospheric particles. But also we have this directly reflected light from the sun, which is also entering in the field of view, or diffuse skylight, which is also reflected within the field of view, and this is the reflected light contribution that we should remove, and also propagated and attenuated through the atmosphere, but also light which is solar light, which is being dispersed in the atmosphere or coming from other the reflection of a pixel outside the field of view, which is collectively called as a path radiance. So these two contributions that can be much higher than the water leaving radiance should be removed if we want to have good results in the algorithms for water quality. And this process of removal is called the atmospheric correction, which is very important in water quality studies. Therefore, what we see is that the observed radiance is the sum of these three contributions, and if we want to obtain the water leaving radiance, we have to subtract the two other contributions. This sangling depends on the angle of observation. Basically, if there is no wind, is determined by the Snell laws of refraction, and if we are observing the water with an zenith angle which is very close to the sun zenith angle, we will have an important contribution of sun length, which is expressed here as the probability, excuse me, the probability, the function of distribution of probability for sangling related with the observation angle. But even if the water is windy, if the water is windy, we can have also sangling at angles that are different from those close to the sun zenith angle, due to the different planes of reflection that are present in the rugged waters. So in the cases of wind-blown surfaces, the range of angles in which sangling can occur it's much higher. This is an example of an airborne airborne image of a lake which has been flown in two different observation angles. In this case, you see this part of the lake in which you can see that the signal from water, the water is quite dark, and this is the polar diagram for expressing where is the zenith and azimuth angles with respect to sun. So here we are in this observing in this part, so let's say in the same side of the sun, and we don't receive almost any sangling. This other image obtained a couple of minutes after in a different observation angle shows a very different picture, and you can see an important reflection of sunlight in the surface. And this could be expressed with those diagrams like this. So in this case, the plane was observing the water in an angle in which it receives a very important amount of sangling. So here you can see 2 pixels in both images, which are in an area apparently not affected by glint, and you can see that the reflectance is very similar, except a little bit in the infrared. While if you see the reflectance of 2 pixels that of the same pixel, affected in one image by sangling and not affected in the other one, you will see a very important difference. So sangling can really affect very importantly the retrieved signal, and therefore it's very important to measure in a geometrical setup that minimizes sangling, and also to correct it in the algorithms for atmospheric correction. So at the end, what we have summarizing is an image. We can say the color image, and several algorithms that through the process of correction of atmospheric effects and the retrieval of water reflectance, and then the retrieval of OCs from reflectance produce thematic map for different constituents. Here is an example of a thematic map of a chlorophyll concentration in a hypertrophic coastal lagoon, the Albufera of Valencia, in which you can see the type of maps that are produced in water quality studies. Well, for ending, I will summarize what are the requirements and which instruments and platforms are mainly used for those water quality studies. So, given all the things that we have said before, the sensor requirements for the study of water bodies are a high sensitivity. So as we saw before, the reflectances of water are typically low, the water level radius are typically low signals, and therefore the sensor should have a high sensitivity and should be optimized. The dynamic range should be optimized for this low range of radiances. Also, it should have a high radiometric resolution. That means that the instrumental noise levels, what is called the noise equivalent radiance or increase of radiance, should be very low, and that means that the signal to noise ratios in the measurement should be high, and obviously with an adequate digitation, at least 12 bit or higher, to have a very good radiometric resolution. And also it's very important, as you saw before, to have narrow spectral bands. To detect the absorption features of phytoplankton and other OOCs, we require bands that those absorption occur in bands that are typically narrower than 20 nanometers. So if we have bands narrow enough, we can use those indexes, those band ratios, baseline indexes or similar indexes, and we can detect and decipher the signal from different absorption features of phytoplankton or other compounds. The importance of a spectral resolution can be shown here. You see in black the continuous spectrum of a given water body as measured with a spectral radiometer, and in blue, for example, you have the spectrum in the right as it could be seen from the thematic matter of Landsat bands, and you see that we lose a lot of information here. This is the example of how it is see with the MERIS sensor, which was on board of Envisat and is the precursor of the Sentinel-3 ULTI sensor, which is going to be in orbit very soon in this year of 2015 or 2016. And this is an example of an airborne sensor with a high number of bands. You see that with an increasing number of bands, we can reproduce more accurately the actual reflectance spectrum, and we can obtain information from those absorption features. You see that with this setup, which is made of only 15 bands but placed in the very interesting part of the spectrum, you can also reproduce quite good the spectrum. Here's an example of the same water body. In this case, it's a reservoir in which water with a high load of sediments is coming from this part, and more clear water is coming from this part. And you can see that the different parts of the spectrum you have different information, and you can see how water is very, very dark in the infrared. But even in this in the infrared, in this case, in the effect of suspended matter could be high enough as to be observed. Well, this last table summarizes some of the most used sensors, satellite sensors used for studying water quality. And the colors indicate how adequate or inadequate could be the sensor for this particular feature. For example, MERIS from Envisat, which was active about 10 years from 2002 to 2012, which is going to be replaced by this ULTI from Sentinel-3, are both two ocean color sensors which have very good radiometric, spectral, and temporal resolution, and also good geographic coverage. And they produce also level 2 products. And it's the same case as MODIS from Aqua satellite. But those three sensors, which are very good for studying ocean waters, are quite limited due to their spatial resolution of 300 meters in this case, or 1 kilometer in this case, so are only useful for very big lakes or medium to big lakes. That this limitation has driven many researchers to use images from land sensors, or from missions that are designed for land studies, which are not as good in terms of radiometric or spectral resolution, especially the old series of Landsat. The new Landsat 8 has an increased radiometric and spectral resolution, and the new Sentinel-2 satellite also has a good characteristics for studying inland water bodies. Those are very good in terms of spatial resolution. Then they can be used for study smaller water bodies. And on the other hand, they don't normally produce level 2 products for water, and the temporal resolution is not as good, especially in the case of the Landsat satellite, which is 16 days, in contrast with the 5 days when the Sentinel-2 would be fully operational, or the 1 day or 2 days of MODIS on OLT. So with this, I will finish this overview of the water quality studies monitoring with optical methods. I hope that this tutorial has been of interest to all of you, and I invite all of you to look at the image processing laboratory webpage, in which you can find more information on this and other aspects of remote sensing. Thank you very much.